Assalamualaikum warahmatullahi wabarakatuh. Today we would like to present our mini final year project entitled Comparative Phytochemical and Morphometric Analysis of Purple Sarmentosum and Lumbergia blue. This study was conducted by the supervision of Dr. Tun Muhammad Firdaus bin Aziz. Next, I would like to introduce our team members for this project. For the first one is Nur Adriana Safia binti Muhammad Hazli. Next is Nur Alia Insyirah binti Ramli. And me, myself, Nur Izzatu Fakihah binti Jamaluddin. First and foremost, for the introduction, purple sarmentosum and lumbergia bleo are ethno-medicinal plants that widely used in traditional medicine in Southeast Asia. Both plants are believed to contain bioactive phytochemicals such as flavonoids, alkaloids, phenolics, and essential oil that contribute to anti-inflammatory, antimicrobial, and antioxidant properties. In addition, for the morphometric characteristics such as leaf length, width, circumference, petiole length, and tone characteristics are frequently used as indicators of plant maturity, environmental adaptation, and phytochemical accumulation. Next, we go for the problem statement. We know that Piper sarmentosum and Lumbergia blue are widely used in herbal practices. Scientific data on the Malaysian Piper sarmentosum and Lumbergia blue plant head and leaf position on morphometric features are limited.
The hypothesis of this experiment is, firstly, morphometric characteristics such as stem diameter, leaf length, leaf width, internode distance, and petiole length of Piper sarmentosum and Lumbergia bleo differ significantly across different stem height. Secondly, Piper sarmentosum and Lumbergia bleo contain a variety of bioactive phytochemical compounds such as saponin, alkaloid, flavonoid, phenolic, tannins, and terpenoid.
We move to the significance of study that are to provide baseline morphometric data at different plant heads, support understanding of plant growth patterns and phytochemical variation. There are two main objectives of this study. For the first one is to measure the morphometric characteristic at different stem height of Piper sarmentosum and Lumbergia bleo. And the next objective is to analyze the presence of bioactive phytochemical compound in Piper sarmentosum and Lumbergia bleo.
We begin our literature review with Lumbergia bleo, commonly known as daun jarum tujuh bilah. This plant belongs to the Cactaceae family and native to regions stretching from Mexico to South America, where it evolved in dry tropical forest. This plant is characterized by fleshy, glossy dark green leaves on the upper surface and pale green underneath. The leaves measures between 6 to 12 cm in length and 2 to 4 cm in width. Its defining feature is the areole. Each areole produces about average 7 spines. The petioles typically range from 0.4 to 0.6, reaching up to 1 cm in larger leaves, with a total circumference approximately 28 to 40 cm per leaf. Next, we look at Piper sarmentosum or daun kado, a member of Piperaceae family. Unlike the previous shrub, this plant is a herbaceous plant originating from Southeast Asia, including Malaysia, Thailand, and Indonesia. Similar to L. bleo, its leaves are glossy and dark green on top, with a lighter green underside. The leaves have an average length of 6 to 9 cm and a width of 5 to 8 cm. The petiole measures between 0.5 to 1.5 cm and the average leaf circumference ranges from 28 to 35 cm. Extensive studies have confirmed that both L. bleo and P. sarmentosum contain bioactive compounds which are saponins, phenolics, alkaloids, flavonoids, tannins, and terpenoids. I will be explaining the methodology. Our methodology is divided into two, which are morphometric analysis and phytochemical screening test. For the morphometric analysis, the stems were collected from P. sarmentosum and L. bleo. The stems were measured and cut into 5 cm sections. Each section was labeled for identification purposes. The leaves present in each section were identified and labeled according to the section and leaf number. For example, section 1, leaf 1 was labeled as 1-1, section 1, leaf 2 was labeled as 1-2, and so on. The number of leaves in each section was recorded. Leaf length, leaf width, and length of the petiole were measured using a ruler. Meanwhile, leaf circumference was measured using a thread, which was then straightened and measured using a ruler. For L. bleo, the areoles present in each section were identified and labeled as T1, T2, and so on. The number of spines produced by each areole was recorded and classified as long or short. Moving on to the methodology of phytochemical screening test. Our phytochemical screening test consists of 3 processes, which are the preparation of the plant sample, maceration, and the last one is the chemical test. For the first part is the preparation of the plant sample. The fresh leaves of P. sarmentosum and L. bleo were washed to remove surface impurities before being sliced into smaller pieces. The samples were placed into containers and dried in an oven at temperature of 60 degrees Celsius and were left for 2 days. After drying, the leaves were ground into a fine powder using a blender. The powdered samples were transferred into 250 ml conical flask for further analysis. The next process is the extraction of bioactive compounds in the samples. The method that we chose was maceration. A 50 ml of methanol was added to each conical flask containing the powdered leaf samples. The mixtures were stirred thoroughly using a glass rod and the flasks were sealed using aluminum foil. Then, the solutions were left undisturbed under a fume hood at room temperature for 6 to 7 days to allow the extraction of bioactive compounds. After the maceration period, the solutions were filtered using vacuum filtration. The extracts were collected, stored in jam jars, and used for the subsequent phytochemical screening test. The last process is the chemical test. First, the extract of P. sarmentosum and L. bleo were prepared in separate test tubes. For most tests, 1 ml of each extract was used. However, specifically for terpenoids, we only used 0.5 ml, and for the tannin test, we used 5 ml of each extract. Subsequently, the chemical tests for each bioactive compounds are conducted as shown in the table provided. The presence of compounds such as saponin, phenolic, alkaloid, flavonoids, tannins, and terpenoids were determined based on the specific indicators and color changes according to the table provided. All the observations were made and recorded.
Now, we will look into the result and discussion of Objective 1. From this table, this is the data morphometric analysis of Loubengler bleo. In this experiment, we observed that the early section of the plant show higher growth compared to the later section. This pattern can be explained by developmental gradients or positional effect within the plant, while growth rate vary depending on the position of the tissue. Younger and actively developing regions tend to allocate more resources to grow, resulting in larger size. Additionally, younger leaves were found to be larger and to have more thorns. These thorns play an important role in protecting the plant from herbivore. The higher thorn density acts as a physical defense mechanism, reducing the likelihood of damage from grazing animals. Furthermore, the presence of more thorns is closely linked to the plant chemical defense system. Leaves with higher thorn density often contain a richer variety of phytochemicals. These bioactive compounds not only enhance the plant defense, but also contribute to its medicinal properties, making younger leaves particularly valuable for medicinal application. We will now look into the data morphometric analysis of Piper sarmentosum. Section with fewer leaves indicate older, mature node where the process of leaf initiation has slowed over time. As the plant mature, energy allocation shifts away from producing new leaf to maintaining existing structure. Larger leaves are commonly found at exposed nodes that receive greater access to sunlight. This increased exposure allows leaves to expand more fully, enhancing their photosynthetic capacity. Leaves with a greater circumference are therefore considered adaptation for more efficient light capture, enabling the plant to maximizing energy absorption under favorable light conditions. In addition, petiole elongation is often stimulated by light competition. When plants experience shading from neighboring leaf or surrounding vegetation, the petiole elongates to position the leaf plate toward better light availability. This adaptive response helps optimize photosynthesis and overall plant growth. We will now look into the result and discussion of Objective 2. This table shows that phytochemical bioactive compound of Loubengler bleo and Piper sarmentosum. In Loubengler bleo, there is a presence of saponin, presence of phenolic, presence of alkaloid, presence of tannin, and presence of terpenoid, but there is an absence of flavonoid. Meanwhile, for Piper sarmentosum, there is a presence of saponin, presence of tannin, and presence of terpenoid, but there is an absence of phenolic, absence of alkaloid, and absence of flavonoid. Compound that present means the plant have high concentration of the compound. It means that when the compound is present, it suggests that the plant is actively producing or accumulating the compound at level that can be identified through analysis. Meanwhile, the absence of a compound means that its concentration is either very low or below the detection limit of the method used, or that the compound is not present in the plant at all. This does not necessarily mean the compound has no biological role, but rather that it may exist only in trace amounts. Overall, the detection of compound provides insight on the plant chemical composition and potential biological medicinal properties.
Next, for the conclusion, we can conclude that both Piper sarmentosum and Limburgeria bleo showed a clear morphometric differences at different stem height. In addition, the leaf size and thorn distribution were generally higher at the middle section, which are section 3 until section 4, that indicating a better plant growth. Furthermore, the presence of bioactive phytochemical compounds in Piper sarmentosum and Limburgeria bleo also was successfully identified through phytochemical tests, which are saponins, phenolics, alkaloids, flavonoids, tannins, and terpenoids.